Let's look at probability distributions. So before we can have a better understanding of the probability distribution, we need to understand what a random variable is. So by way of definition, a random variable assumes numerical values that are determined by the outcome of an experiment. We often summarize the outcome from a random experiment by simple numbers. So in many of the examples that we have looked at so far, in fundamentals of probability theory, the sample space has been a description of possible outcomes. So in some cases, we have the descriptions of outcomes being sufficient, but in other cases, uh, it is useful to associate a number with each outcome in the sample space. Now, because the particular outcome of the experiment is not known in advance, the resultant value of our variable is not also known in advance. So for this reason, the variable that associates a number with the outcome of an experiment is what we usually refer to as the random variable. So we are not going to go so deep into what the details of a random variable, but we just need to understand what it is so that we can use it in our examples. We can demonstrate using the probability distributions. So we can have discrete random variables, and we can have continuous random variables. Why the distinction? Now, if x, which let's denote x as the random variable. Okay, so if x is a discrete random variable, then it takes only a countable number of values. This means in practice that we may consider a list of possible outcomes. For example, let's start x as say 0, 1, 2, 3. So this is an example. So we can have the counting continuous up to infinity. So with this one, we can actually have a list. We can count up 0, 1, 2, 3. So this is what we call the discrete random variable. The probability distribution, or simply let's just call it a distribution, unless we want to stress on the differences. So we can just call them the distribution of a discrete random variable. X is a table or a formula that lists the probabilities of each outcome of the random variable x. So this is an example of a discrete random variable. Now to talk about continuous random variable, it has to take a range of numbers. Let's say from 0 to 3. This is a range from 0 to 10. This is a range. So we can denote the range like say we have x is between 0 and 3, something like that. So with this particular one, we can't count all the numbers. It is impossible to count every single distinct number within this range. So that is what we call the continuous random variable. So somebody can say, okay, what about 0 to infinity? How do we count it? It is not going to be possible for us to count 0 to infinity. I don't know how long it's going to take us to do that. But the range, it is impossible to count. Now that we know what the random variables are, if the random variable is coming from the discrete category, then we call that the discrete probability distribution. If it is coming from the continuous category, then we call that the continuous probability distributions. So in this our tutorial, we're going to concentrate on basically on the discrete probability distributions, so that in another video we can take the continuous probability distributions with examples. The probability distribution of a discrete random variable x is described as the function. So this is the function that describes the probability function, okay, or the distribution. So we call this the probability mass function. So this is where we say, okay, the random variable x, we have it here. So what is the probability that this random variable? So the association of the random variables with their respective probabilities is what we call the probability distribution function. And because it is a discrete function, we call that the probability mass function. So examples of discrete probability distributions, there are a number of them, but we are just going to consider these two, a binomial distribution and a Poisson distribution. So in the binomial distribution, you only have two possible outcomes. Okay, let's say success or a failure. Now, a success in this case do not necessarily mean the English definition of a success. So it is simply what we are interested in. So if you are looking at the probability of students failing a particular subject, then the failure of this subject becomes the success in this case. If you're looking at the number of defective items that is shipped down to your store, then the defective items become the success, the expected values and the variance. If we draw the table, like say x, so we have 0, 1, 2, so this is just an example with their probabilities, let's say 0 0.2, 0 0.15, 0.5, 2, 0 0.3, 0 0.5, 0 0.6, so it's 0 0.4. So the sum of these should give us 1. So let's take, for example, that this is what we have as the probability distribution. So we would be interested in the expected. What would be the average outcome of whatever we're looking for at the end? So expected value says that take a random variable, multiply it by its probability value. So in this case, we are going to have 0 multiplied by 0 0.2. That is for the first one, and the second one is 1, so 0.5. So we do like that until the last one, 0.4. Okay. Now, if you do this, these are individual. So, what is the total expected value? We need to add all of them. Okay. So, adding the four values will give us the expected value. So, basically, what the expected value of a random variable is all about. Now, when we come to the variance, variance has to be indicated in this statistics. So, let's say this is what we have. I'm just giving a minimum here and then a maximum here. Okay, so we are looking at here, we have linked all the values, the values that are there, and this is the average. So, what is the average distance between the values, the individual values, and the mean? Alright, so let's take an example of a probability distribution. We have x as our random variable, and then the probability of an x is what we have there. So what is the probability of getting a 2 or a 4 from this particular example? In probabilities, when you see the word or, what it means is that we have probability of 2 plus probability of 4. So what is this particular value? We already know where the 2 is, we know where the 4 is, and the respective probabilities. So probability of the 2 equals, and then probability of the 4 is equals to 0.2. So probability of a 2 plus probability of a 4 is equals to 0.2. So this will give us 0.35. So this is the probability of getting 2 or a 4. What is the probability of not getting a 1? Now with this one, I want to show you how we're going to do it. I will demonstrate it using the number line. So we know that if we sum all the probabilities here, from the first one to the last one, we get 1. So if you sum that and you don't get a 1, it means there is something wrong. It is not a probability distribution. So in effect, I'm going to say, all right, this is from 0 to 5. Then they are asking us to find the probability of not getting a 1. So 0, 1, 2, 3, 4. So 1, 2, 3, 4, and 5. We are going to cut this out and find probability of the rest. So by way of notation, we have probability of x not will be equal to probability of 0 plus probability of a 2 plus probability of a 3 plus 4 plus probability of 5. Now, this is going to take a very long time to solve. Probability of getting one is just this, which we have in the table 0.2. Okay, that is simple. So I'm going to go back to the table and say the number line, okay, and say that, okay, this one, if I do this, I will just call this one. That is the sum of all the probabilities. Unfortunately, I don't want all of them. I want to cut part away. And this part is called 0.25. Now it's going to be left here and then the side. Okay. So it means that it's plus 0.25 plus the y should get 1. Now x plus y in this case is what we call x equals 1. So what does that mean? It means that I can actually find the 1 that's minus probability given the demonstration in the number line. So once I know the probability of x equals to 1 is 0.25, I just do my subtract 1 minus 0.5 give us 0.75. So this is how you can solve this particular question. Now let's look at the next one. Using the same data as we did earlier, calculate the mean, the variance, and standard deviation. Now the mean is the same as the expected value. Okay, when we say mean is the same, and we did expected value earlier on as summation of x multiplied by x. Let's construct the table again and then find this inside the table. It makes it easier and the solution compressed. So I'm going to reconstruct the table this way, then put then 0, 2, 3, 4, 5 with their respective probabilities 0.2, 0.25, 0.5, 0.1, 2, and then 0. So I have here the probability of x. What do we do there? What does that mean? Now the x and p of x, I'm simply going to multiply the two of them. Okay, so if we are going to do that, what are we going to get? 0 multiplied by 0.2, that would be a 0. 1 multiplied by 0.25 would be 0.3. 2 multiplied by 0.15 would be 0.3, and 3 multiplied by 0.1 is 0.3. So this is basically how you're going to do the multiplication. So watch your calculators and you have these values. So I can be wrong, so do well to cross-check using your calculators. Okay, so the expected value, when I go up here, expected value of x now be the summation this column called x multiplied by p of x. So sum all of them as 0 plus 0 to 5 all the way to 0. So if we punch in our calculator, we should be able to get something like this. So this becomes the expected value of x given the data in the table above. Now, how do we get the variance? Variance, we said variance was expected value of f minus expected value of x all squared. Fortunately, we have gotten expected value of x. So the square of that goes to 2.15 squared. So this is the expected value of y. So we get approximately 4.6. So that is the expected value of x squared. What we are left with is expected value of x squared. It is not different from what we have done already with the expected value of x. So expected value of x squared is simply equals to sum of x squared multiplied by x, probability of x. So let's go back to the table and have here x squared p of x, so that we are going to have 0 squared 2, then this is 1 squared divided by 0.5, 2 squared divided by 0.1. So this is what you're going to do for all of them. 5 squared 0.1. So if we do this rightly, if we do it correctly, then we should be getting again, this will be 0. 0 multiplied by any number, we should be getting 0. So 1 square is still the same 1, so our value here will not change. 2 square multiplied by 0.15 will give us 0.6. Then 3 square multiplied by 0.1 will give us 0.9. Then we have 2.5. So again, we are going to add this particular column, and that is the column we call sum of x squared multiplied by probability of x. So our variance of x now will be this, the summation of this, which is approximately equals to 7.45. So we're going to have 7.45 minus what we already calculated here, 4.6. Then it should get approximately that's 8, something like that. So this is the variance. How do we get the standard deviation? The standard deviation is simply the square root. So standard deviation is the square root of x. So square root of 2.83. So find the square root of this one value, and we should be targeting to come to the top here. So standard deviation is equals to 1.682 or something close to that. So this is how we calculate the mean, the variance, and standard deviations of a probability distribution. Now let's take an example of the binomial. We said the binomial was x, so we have n choose x. Probability of a success raised to power x. Probability of a success raised to power minus 1. So this is the probability at the formula or the probability distribution of a binomial. Now the example is this. John manages a company that distributes bolts and nuts. From previous experiences and feedback from retail stores, the manager notes that the probability of a bolt being faulty among those scheduled for distribution is 0.3. Our job here is to find the probability that in a random sample of 20 bolts, there are exactly 2 faulty bolts. How do we handle this equation? So we know this is a binomial. Okay, so we can denote it as binomial, then NP. This is a way of denoting or representing the binomial distribution. So X follows this particular distribution. Now let's look at how we can calculate it. What is n in this case? In the question we have n to be 20. Okay, n is equals to 20. What is p? P is the probability of a success, which is equals to 3. So we have our x is binomial with 20 trials and probability of success equals to 0.3. So before I come to solve this, let's look at the properties of a binomial. You will need that to help you identify what a binomial distribution is, or when you get a question, you should be able to identify and get the parameters appropriately. So the binomial distribution describes the behavior of a count variable x if the following conditions apply. 1. The number of observations n is fixed. So you're going to have, let's say, n number of trials. So this n number of trials is fixed. Each observation is independent. Third one is that each observation represents one of 2 outcomes. So in every trial or in every experiment, you expect 2 outcomes which are the same. One is a success, the other is a failure. Okay, so if we are looking for a 6 in a die, either you get a 6 or you don't get a 6. If you toss a coin, either you get heads or you get the tail. And the probability of a success, P, is the same. So coming back to our question about getting exactly to both, let's see how we can handle that without a problem. So probability of x, so exactly 2, will be equals to the n choose x will be 20 choose 2. So we have 20 choose 2. Then our probability of a success is 0, 3 raised to the power 2. 1 minus the success. This is a probability of a failure. So 1 minus probability of a success is a failure. So we have 20 minus 3 here. Okay, so let's see. How do we get 20 choose 2? If you are using a calculator, that is fine. It is easy to get it. But if you are not using a calculator, let's see how we can do that manually. So we have 20 factorial all over 20 minus 2 factorial multiplied by 2 factorial. Okay, so this is equals to 20 factorial all over 8 factorial factorial. So we want to expand the factorial. Factorial is simply means that we're going to have the 20 factorial simply means that we're going to have 20 times 19 times 18. So you're reducing by 1 until we get to 1. Okay, the product of all those numbers. So we have 20, 19 multiplied by 18 factorial, all of 18 factorial by 1. So this is your 2 factorial, and the 18 factorial we are not expanded it. Now the reason why I stopped at 18 factorial is because I have 18 factorial down there. So if I'm going to expand this, I will get exactly the same as that. So I'll just leave it as it is and cancel the 2 out. Okay, so but the 2 here, we have 2 and go into 20 10 times. So what we are left with is 10 equals 190. So this is 20 choose 2. So let's put that in formula. Then we have 0 multiplied by 0 0.3 raised to 2 multiplied by 0.7 raised to 18. So do the calculation, we will end up with 0.008. So this is the probability of getting exactly 2 faulty bolts. The second question is, what is the probability of getting more than 3 faulty bolts? Now, this one I have demonstrated already somewhere in a number line. Okay, something like this. Say, okay, we're going to have here as from 0, because we can have 0 bolts, 0 faulty bolts, and we can have all 20 being what faulty. The question is more than 3. Let's put 3 here. So more than 3 will be here. So probability of 4 plus 5 all the way up to inch. So this is a very long way of calculating it. Now from 0, probability of 0, probability of 1, 2, probability of 3 looks somehow simpler and shorter than starting from 4 to 20. So if I am going to have this is going to be a 1 value. Sum the other ones, and that will also be 1 value. Let me call this x and call this y. So again, as before, x and y should get 1. That is the total probability of the sample space. I can find this short one very easily, but this long one is going to take me time. So I would rather go for the first one, which I do not need. Okay, so the first one is probability of x less or equal to 3. The second one is probability of x greater than 3. That is from 4 up to 20. The total of this will be equal to 1. Now, what I am looking for is the probability of x greater than 3. So let's let that stand alone. X greater than 3 minus probability of x less or equals to 3. So basically, this is what we are going to use to solve this question. Okay, x greater than 3 equals 1 minus equals to 3, so that we can have probability of less or equals to probability of 0, that is not having any fault bolt at all, probability of 1, probability of 2, and probability of 3. This is very short and simple. So put the values into this, then we have 20, 0, then I'm just putting the values 0.3, 0, 0.7, that is 1 minus 0.3, then we have 20 on top here. 20 minus 0 is the same thing as 20. Then we have 20 choose 1 is the next one. The probability is 0.3 raised to the power 1, then 0 raised to the power 19, plus 20 choose 2, probability of success 3 raised to the power 2, multiplied by 0.7, that's the probability of a failure, raised to the power 18, plus 20 choose 3, multiplied by probability 3 here, plus 20. Now let's use our calculator to find the values here. Okay, so if you point your calculators, we should be getting for probability of 0 is equal to 0.000300798 plus probability of 1 is 0.00684, as probability of a 2 is equal to 0.0278, then probability of a 3 is equal to 0.071604. So if we sum all these, let me go to the top here. So we sum all that, we expect to get 0.10704. Okay, but then we are looking for probability of x greater than 3, which is minus that figure 0.0704. This will give us 0.893. Okay, so this is the probability of getting more than 3 to be faulty, about 89.3%. Example 3. Still on the binomial distribution. Let's look at this example 3. In the wake of unemployment in the country, several graduates from polytechnics and technical universities resort to establishing their own businesses. However, these businesses do not stand the test of time due to inadequate funds to support the growth of business. Suppose 10 graduates established their business independently over the last few months. What is the probability that 4 of the 20 new businesses will flourish at the end of the year, assuming 40% of businesses exceed? Probability of a success. So reading through the question, we see at the end that assuming 40% of businesses succeed. So that is 500. 40 divided by 100 is 0.4. So we have a probability of success which is equal to 0.4. So let's state our formula as 4 equals to n choose then x minus 3 minus x. We know what n is. N is equals to 10 according to our question. That is, suppose 10 graduates establish their own businesses. And what is 4? Where do we find the 4? What is the probability that 4? What is the probability that 4? So x is equals to 4 in that case. So we have random variable equals to 4. We equate that to 10. Probability of x is 4 to the power 4 multiplied by 1 minus 4 is 1 minus 0.4 is 0.6. So 0.6 raised to the power 10 minus 4. That is again 6. Okay. So do your calculations as we did earlier before, then factorial all over, then minus 4 factorial. So this will give us by 9 by 8, 7 all over factorial by 4 2 and 1. So if we do our calculations, we'll end up with 2. So n choose 4 is equals to 210. So we put that back into our formula and we have 210. Then 0.4 raised to the power 4 is equals to 0.026 multiplied by 0.6 raised to the power 6, 0.04666, and point your calculator, the total to be this. Okay, so let's focus our attention on the Poisson distribution, which is also another discrete probability distribution. Experiments yielding numerical values of a random variable x. The number of outcomes occurring during a given time interval or in a specified region. So the Poisson distribution considers numerical values of a random variable that is within a time interval. So an example of these time intervals could be minutes, could be hours, could be days, could be weeks, could be months, or even a year. So these could be individual intervals for the Poisson distribution. For example, a Poisson experiment can generate observations for the random variable x representing 1. The number of telephone calls received per hour by an office. Another example is the number of days school is closed due to a pandemic, just like we had the COVID-19. So how many days did it take us to go back to the classroom from virtual studies? If it is not the COVID-19, if it is an outbreak of cholera, and they say, okay, let's stay at home. If the children come together, they probably would contract this cholera. So let's stay at home until everything is okay. How long are we going to stay at home? How many days? So that could generate a Poisson distribution. The next one is the number of games postponed due to rain during a soccer season. We know in this part of our country, our stadia are open top. So if it is raining, we will have to postpone because we cannot play in the rain. So how many of such games are postponed due to the rain? So these examples generate Poisson data. Okay, so a Poisson distribution is obtained from a process, a Poisson process. And what are the properties of this Poisson process? One is that the number of outcomes occurring in a one-time interval or a specified region or space is independent of the number that occurs in any other disjoint time interval. So if we have, let's say, functions that come to work at 8 a.m., let's say, and close at some close at 3 p.m., others close at 4 p.m. So we want to look at from 8 to 9 to 10, 11 up to 3 o'clock. So within every 1 hour, how many customers visit the bank? So the number that is coming within 8 to 9 is not dependent or it's independent of the number that is coming here. So you cannot say that because people came within 8 to 9, which is 1 hour, then we should take the same 10 coming between 9 and 10. No, these two outcomes are completely independent of each other. The second one is that the probability that a single outcome will occur during a very short time interval is proportional to the length of the time interval or the size of the region. Let's go back to the same example again, 8 a.m. to 9 a.m. This is big enough for a lot of people to come in. What if we decided that, okay, we are looking at it in minutes. So from 8, we are looking at 2 minutes interval. That will be 8, 2 minutes plus 8, and 8, 4 in that one. So within these 2 minutes, you won't have a lot of people coming in. So if we want to take the probability that probability of people coming in within this short period, it is very, very small, very minute, that we can just throw away without having to worry about it. The third property is that the probability that more than one outcome will occur in such a short time interval or fall in such a small region is negligible. Yes, I think I've already mentioned that in the second one. Now let's take an example on the Poisson distribution. A procurement officer is studying the distribution of a newly branded biscuit in the market. The market is divided into a number of equal segments. The mean number of branded biscuits per segment is assumed to be 3 purchases per every 1 hour interval. The branded biscuits are distributed randomly to the stores throughout the market. Find the probability that in a randomly chosen market segment, there will be more than 2 sales of branded biscuits. This is the question. Find the probability that in a randomly chosen segment, there will be more than 2 sales of branded biscuits. Now the Poisson distribution is called these successes is equal to e to the power negative lambda multiplied by lambda a. Now from the question, it will mean that we find the value of lambda. How do we get the value of lambda? Let's go back again to read the question on the second line. The end of the second line that says the mean number of branded biscuits per segment is assumed to be 3 purchases per every 1 hour interval. So this is equals to your mean 3. So what is the probability that more than 2? So we can take it more than 2 as p of x greater than 2. And I'm sure we have seen this over and over again. We have so many biscuits in the market, you can't finish counting. So if you are going to say greater than 2, it will mean we have to plus 4 with 4 up to a number that we don't know. Okay, there are so many biscuits in the market, so we cannot count. But we know that if it is not greater than 2, then it must be less than or equal to 2. So we want to say that x or equal to 2 greater than 2 is an overlapping. If we add them, probability of 1. So why don't I find this probability of x less or equals to 2 so that my probability of x greater than 2 would be obtained from this equation. Yes. Something like that. So this becomes easy. Okay. So we have equals to 1 minus, then I put my color bracket, probability of 0, 1, probability of 2. Okay. Minus. Now we put this inside. How do we determine that e raised to the power our expected value, which is the mean, minus 3 multiplied by 3 raised to the power 0 all over 0, 2, plus the next one is probability of a 1, e to the power negative 3, 3, 1, plus p of 2, that's probability of getting a 2, to the power 3, negative 3, 3 to the power 2. So this is the calculation that we are going to do. Getting 1 minus 0, 0, 0, 8, sorry, 4, 8 plus 0.1494, 149 plus 0.22. Alright, so we do the mathematics here because x greater than 2 equals to 0.768. Put this in percentage form, we have 57.68%. On the same question, we are looking at the probability of getting either 5 or 6 sales of branded biscuits. Now again, we go back to 5 or 6 formula, which is equals to e to the power, the expected value is 3, so 3 here, multiplied by 3 to the power 5, or factorial, or here it's okay, so e to the power negative 3 multiplied by 3 raised to the power 6 all over 6 factorial. So this will give us what is on top there, 12.0983 over 5 factorial, 5 times 4 times 3 times 2 would get 120. Then we add that to the second 36.2948 all over 20. So sum this 2, then we end up with 0.112. So this is how we calculate the probability of getting 5 or S6 from the example that we just worked. We could use the Poisson distribution table to find the probabilities. So let's try that and see. If we want to use the table to answer this particular question, we probably say is the same as x less or equals to x minus x or equals to 4, because 5 is included. This is the Poisson table, Poisson distribution table. We have the lambda, that is our mean to be 3. We have the first one here. We have this. Then we need this one too. So the probability of getting p x less or equals to 6 is equals to this first one here. Then probability of x less 4 is what we have here. Let's go back to our example here. So this is equal to 0.6 minus 0.8153. Let's confirm. Yes, 8153. So this is how we would have calculated this. And the subtraction, we have 0.1. So you can see that the answers are the same, but we're using different methods. Let's look at example number 5 on the same Poisson distribution. A factory produces components of which 1% are defective. The components are packed in boxes of 10. Using a suitable approximation, find the probability that a match of 250 components contains between 1 and 4 inclusive defective components. Now, if you look at this so carefully, this would have been a binomial case, but then we can use the Poisson distribution to approximate the binomial distribution. So let's see. If this is a binomial distribution, then we expect a n, we expect a p. So our p is equals to 1%, 0.01, and our n is 10. So we have n equals to 10. But then we have an interval between this, between 1 and 4. So we want to use the Poisson distribution. We want to use the Poisson distribution to approximate the answer to this binomial situation. So the relationship between the mean of the Poisson distribution and that of the binomial is that the mean for the binomial, which is NP, is the same thing that we are going to use here, NP, and give that answer, that value to lambda. So our lambda is equal to n multiplied by 0.01. Okay, 0.01 is the 1%, which is equal to 2.5. So we can now go back to the Poisson and say, okay, I want the value that is between this 4. So this is equals to probability of x less or equals to 4 minus probability of x less or equals to 1. Now, you remember the other place what we said about this fund. If we were to do the manual way like we were doing, we will include 4. So, 2, 3, 4. So if we say probability of x less equals to 1, uh, we are going to include this, which is going to be removed. But then our reading should start from less or equals to 0. So let's go to the table and try to read this to see. So we need this less 4 means or equal to 1, which we are not going to read exactly at that point. Okay, so let's see the 4. Our lambda is 2.5. So we have 2.5 here. Then our x, what is our x is 4. So we come all the way down to this point. Okay, 0.8912. Let's write that there before we forget. 8912. So this is x less or equals to 4. Let's go back to the second one. If we are reading this, it means that we're going to remove this one. But then 1 is included in the calculation. As we saw in the question, it's inclusive, 1 to 4 inclusive. So it means that we will have to take minus 1 from here and read from x less or equals to 0, which is 0.0821. So we have 0.0821. Hence our answer is 0.8912 minus 0.0821. That will give us 0.809. So the probability of probability that a batch of 250 components contains between 1 and 4 inclusive defective components is about 80. Yes. This video is getting so long, so let's take one last example and we break it from there. Professor Ahmed encourages his quantitative method students to act in a prudent manner by consulting the professor if they have any questions as they prepare for the exam. It appears that students' arrival at the professor's office is a Poisson distribution with an average of 5.2 students every 20 minutes. Professor Ackland is concerned that if too many students need the professor's services, a crowding problem may develop. So the professor is expected to determine the probability that 4 students will arrive during any 20-minute interval, which could create a crowding problem that Professor Ahmed fears. If this probability exceeds 20%, a second tutor or second professor will be hired. Alright, so let's examine this probability at x4. We get our formula in play. Negative lambda x all over. So we have expected value of negative 2 2 raised to the power 4 all over 4 factorial. So this will give us somewhere 0.68. So approximately 16.8. The condition here is this. If the probability we have calculated exceeds 20%, then a second teacher needs to be hired. But then looking at the solution, so we can say in a 20-minute interval, the chances that the professor will receive 4 students is approximately 16.8%, which is less than the 20% threshold. Therefore, there is no need to hire a second professor for this service. Alright, so let's look at the second part of this question. More than 4 students will arrive during any 20-minute period if the probability is greater than 50%. If the probability is greater than 50%, then the professor or the tutor's office hours will be extended. Now here we expect to find the probability that more than 4 students will arrive at the professor's office. That is greater than 4. Because we do not know the maximum number of students involved here, we cannot determine where to end. If we are going to say probability of x equals to 5, 6, 7, after that, now we cannot determine where we are going to end. So what we need to do is to calculate the cumulative probabilities from when no student arrives. That is probability equals to 0 up to probability equals to 4. Then we subtract that from 1, then we get what we are looking for. So this equals to 1 minus probability of this equals to 4. Because 4 is not included in what they are looking for. So this will be equals to x, so p of 0 plus 1, 2, p of 3, and then number is the same thing, but 2 it hasn't changed, 5.2. So we're going to use this 5.2 to run through all of these. So we have e next 2 by 2 to the power 0, or Victoria plus e negative 2, 2 to the power 1 all over Victoria up to 4 e 5.2 multiplied by 2 is 4 for factorial. So we're going to do this for each of them, and at the end we expect this value 0.0052 plus 0.028 0.028 plus 0.0745 plus 0.12928 plus 806. If we add all these, we should get 0.406. So we come back to the probability of which minus this total that we have 1.3 will give us 0.593. So we're going to have 59.3%. Now the conclusion in this question said if this probability we are going to calculate is more than 50%, then the professor's office hours will be extended. So from these results, the professor's office will be extended. Why? Because the probability that we have calculated that more than 4 students will arrive at the tutor's office is more than 50%, which is 59.39. So office hours will be extended. So that is how we calculate the probability for this particular one. So the last but not the least, 7 students arrive during any 30-minute interval. If the probability exceeds 30%, then Professor Ahmed himself will offer additional tutorial. So all along we have been looking at 20% interval. This time is 30%. How do we convert it back to the 30%? So the 20-minute period that we have, so the conversion that we are going to do, our lambda is equals to the new interval multiplied by the whole rate, that is the lambda, all over the whole interval. Yes, 7.8. Okay, so our new lambda is going to be 7.8. So what is the probability of x? 7 students arrive during any 30-minute interval. So what is the probability of x equals to 7? So we have e raised to the power negative 8 multiplied by 8 raised to the power 7 all over 7 factorial. So put this in the calculator and we get 0.178. convert it to percentage multiplied by 100. 8. If this if this percentage exceeds 30%, then Professor Ahmed himself will have to offer additional tutorials. But looking at the result, looking at what we have, Professor Ahmed need not offer any additional tutoring since the probability of receiving such students in a 30-minute interval is 15.78, which is much less than 30%. This will end our discussion on discrete probability distributions, focusing on binomial and Poisson distribution.